Hello YouTube, this is part 5 of how to build a Raytracer from scratch in C++. In the last video, we extended our Raytracer to model a camera and light in 3D space. And the way that we did that was by declaring a class for our camera and a class for our light. But those needed some more fundamental classes, such as the vector class, the ray class, the color class. So once we had our vector class, we needed to define some method functions to perform some standard linear algebra, like normalizing vectors, dot products, cross products, adding and multiplying vectors by scalars. But I noticed a typo in my dot product. The dot product of two vectors is the x component of the first vector times the x component of the second vector, plus the y component of the first vector times the y component of the second vector, plus the z component of the first vector times the z component of the second vector. So that y needed to be a z. And then once we had these method functions, we were able to do the linear algebra that we needed to orient our camera in a way that would be convenient for perspective later on. So we defined the position of the camera and where we wanted our camera to be looking at, and then we created a new vector which was the difference between these two vectors. So the x component of the difference vector is the difference between the x components of these two vectors. And then with the y and z, I noticed that there was a typo here. The z component of our difference vector needs to be the difference between the z component of the camera position and the z component of the location that the camera is looking at. So this y needs to be a z as well. So now we're ready to model a sphere and plane in 3D space. And since we use classes to model camera and light, obviously we're going to be using classes to model spheres and planes. But in 3D space, the only thing that a sphere needs to be modeled is a location for the center of the sphere and the radius. That's all that a sphere needs to be modeled in 3D space. So we're going to create a new class . Then we're going to copy our light class as a template. Replacing light with sphere. So for our sphere, we're going to give it a vector for the center. We're going to give it a radius. And since we have this nice color class already set up, we're going to give spheres a color. Method functions are now get sphere center, sphere radius. Get sphere color. We want our default location for any new sphere in our scene to be the origin. We're going to give it a default radius of 1. And we'll let our default color be gray. So you noticed that earlier we modeled color with red, green, and blue values. We're still doing that here, except sometimes we want to model color as red, green, and blue values that range from 0 to 255, and sometimes we want to model color as a value that ranges from 0 to 1, where you can map 0 is equal to 0 in both cases, but 1 is equal to 255 in the other case. Where gray would be 0.5 in this version of color. And we'll let the special value remain 0 for now. So we can provide the center, the radius, and the color manually when we declare new instances of the sphere. So we have to tell it to expect that. Go ahead and compile. Hopefully we won't have any errors. Great. So now we have the sphere class, and we can declare new instances of spheres in our scene. We're going to give it the origin, which we need to declare that vector in a second, as the location for our scene sphere. We're going to give a radius of 1, and let's let the color be this pretty green color that we created. So let's declare the origin vector. A capital O, where O is just a vector that corresponds to the origin of the scene. So this line declares a new instance of the sphere class. The instance name is scene sphere. It's located at the origin. It has a radius of 1, and we're going to give it this pretty green color that we defined here. Let's compile, make sure we don't have any errors. So we're not going to be able to render out the sphere until we define a few more things, and those are going to deal with how object-oriented programs like there to be sort of a root class, and that root class we're going to call object. So we need to create a new class called object, and any object in our scene is going to be a subclass of the object class. We can use our sphere class as the template. Replacing sphere with object. Object class is eventually going to need the ray class. The object class doesn't have any parameters to its default constructor functions. So an object is simply an object. But if an object happens to be a sphere, we want to be able to get the color, say for instance, of the sphere. So what this is doing is, when we have an object like a sphere, if we want to get that object's color, there's going to be some interesting things that happen, and those have to deal with creating shadows. So when a ray tracer looks out into a scene, looks through its camera, past an image plane, and looks into the scene and determines what objects are in that scene. So for instance, if a ray comes out of the camera and intersects with the sphere, the algorithm that all ray tracers follow is you go directly from the point of intersection to your light source. So if you intersect the sphere on one side and it has to pass through the other side of the sphere to get to the light source, then the point that it's been intersected should be in shadow. So for right now, we need to finish this object class. The other thing we want our object class to do is to be able to return the intersection that a ray makes with an object. So we're going to define a new method function that we'll be seeing a lot of, and that's called find intersection. And for a null object, it's always 0. So the object class is our top of our hierarchy, where all objects within our scene become subclasses to the object class. All objects should have a color. All objects should be able to intersect with a ray, and then we're going to be finding intersections with rays and objects. That's one of the most complicated parts about a ray tracer, is when you create a ray, which is a vector, and you want to find the intersection between a ray and a sphere, for instance, you have to do some pretty intense linear algebra. We're not going to do that yet. That's going to be additional method functions that we're going to be adding to our sphere class. For right now, let's compile. Now that we have our object class, we're going to go back into our sphere class and tell it that all spheres are going to be subclasses of the object class. Simple enough. Compile. And now we're ready to model a plane. We can use our sphere class as our template. Lines in here first. Get a new file. Save as plane.h. Paste our sphere class in there. Replace sphere as plane. But the way that we define spheres in 3D space obviously is not with a radius. All that we really need to define a sphere in 3D space is a normal vector, which, if you're not familiar with normal vectors, a normal vector is a vector that is perpendicular to our surface. And instead of a radius, all planes have a distance from the origin. So let's say you have an arbitrary plane in 3D space. That plane's going to have a normal vector which orients the plane, and then it's going to have a distance from the center of our plane to the center of our scene. And of course, planes can have color too. Method functions become get plane normal. distance. Color. We'll let the default plane normal direction be in the X direction. So what that's saying is that the default orientation for a plane that we create in our scene, if we don't define the normal vector, it's going to be in the X direction. So for our purposes, X is up. Z is going to be depth into our scene, and of course Y would be left and right. Default be at the origin. And we'll let the default color for planes be gray as well. These become normal value, distance value, color value. Pile, around the arrows. Uh-oh. Forgot to remove center somewhere. So planes have normals and distances, but we need to add some more method functions because planes are quite a bit easier than spheres when it comes to finding intersections between rays and planes, and when it comes to returning the direction that the ray, the reflection, right? So when a light ray reflects off of a plane, it's much simpler case than when light reflects off of a sphere. So the way that we calculate these reflections is by getting the normal of the point that we intersect. So for a plane, the normal vector at the point of intersection is going to be the normal vector for the entire plane throughout. So it doesn't matter where a ray intersects our plane, the normal vector at that intersection is going to be the normal vector of the plane. So we create a new method of get normal at. And the normal at a particular point on a sphere is going to be the normal of this whole plane. Sorry, I think I said sphere. And the way that we find intersections between rays and planes is with the find intersection method function. So the class of a ray is called ray, but we're also letting the individual ray that we're trying to find the intersection of, called ray. Where the ray that's being intersected with our sphere has already been defined somewhere else in our program, usually through a perspective routine. So once our ray comes into our scene and intersects with a plane, that ray has a direction which has already been defined. We just need to get that value. The reason why our find intersection method returns a scalar value is because you can think there's always going to be a distance from, let's say, the camera where the ray originates and the point of intersection. So if a ray has a direction and it goes out into our scene, it's going to go out infinitely in that direction. But if it intersects something, it's not going to be infinitely in that direction. It's going to stop and terminate at the intersection point. So the double here means the distance from our ray origin to the point of intersection. You define the dot product between the ray direction and the normal vector, which is a scalar. So A is the dot product between the direction the ray is coming from and the normal vector of our plane. And if that value is 0, that means that our ray is parallel to our plane. So if our ray is parallel to the plane, and the find intersection method is trying to return the distance to the point of intersection, but it never intersects it, we want to return a negative value, and that's going to be a condition we can use later on to determine if a particular ray intersects an object. If it returns a negative value, then it doesn't intersect. Otherwise, the distance that the find intersection method is going to return is defined as follows. So D is a value, which is the dot product between the normal vector and another vector, which is the result of some linear algebra. And the vector that we're dot product with our normal vector has components that is in the opposite direction from the origin from our ray, so it's in the opposite direction than our ray, and it is the multiplication of the distance normalized added to the ray origin and then reversed. So it's a complicated sounding thing. It's really not. Where -1 times b over a is the distance from the ray origin to the point of intersection. Compile. There we go. Now we're ready to create an instance of plane in our scene. Where we're going to give it the y-coordinate or y-vector for our normal vector. We're going to let the distance from the center of our plane to the center of our scene be -1, which means if our sphere is located at the origin and it has a radius of 1, we want to place the plane directly beneath this sphere. So that does mean that y is the up direction as opposed to x. So y is the up and down direction in our scene, z is the depth back and forth in our scene, and x will be the left and right coordinate. And let's let our color for our scene plane be, let's create a new color. Create a color maroon. We'll definitely come back to this special parameter later. That's going to be how we add reflectivity and various levels of shininess and dullness to our surfaces. And let's let the plane color be file. So now we have a ray tracer which models a camera, light, objects such as spheres and planes, and then we're going to be getting into the real meat of the ray tracer, which is the routines that loop through our objects, determine the intersections between the rays coming out of our camera and those objects, determining which objects are in front of other objects, and then how we create shadows by tracing directly from our point of intersection to our light source, and then determining if there's anything in between the intersection point and the light source which would create a shadow. And that's what we'll do next time. So I hope you stay tuned, and thanks for watching.